Okay, so thank you very much. My name is, as Gabriela said, Joaquim Pinto. I'm a professor of meteorology in Karlsruhe Institute of Technology in Germany. And he asked me to show a bit of the work we have been doing on how we can use our knowledge of information about climate change, climate extremes, actually to inform adaptation measures. Okay. Thank you. So, okay. So a bit about of the background, what we are doing. So probably all of you have heard about IPCC and CMIP models, and typically the global models that are used for these experiments have even nowadays a resolution of over 100 to 150 kilometers. So if you think about like a summer day in a city like Hamburg, this is what it looks like in a climate model here on the left side. So you are looking at boxes 150 or 250 kilometers, so you don't see the city. So this gets a bit better if you go to what we call regional climate modeling. So you do a first downscaling to about 12 kilometers. And then you're starting seeing some detail, but even then, you do not see the city. And it's a city with over 1 million persons, right? So it's only when you go to resolutions of about 2 to 3 kilometers that you start seeing the details. And in particular, in this case, and this is what is shown in the figure, you see the heat island of the city of Hamburg. You see that the surroundings that is a bit cooler, and you actually also see the Elbe River. And this is what we call convective permitting modeling, that we use very high resolution modeling that enables us to get much more information on the regional scale, and also that they are also more physical based because you need less parameterizations at this level. So just very shortly about a background, just to try to convince you that this is actually useful. This is a figure from a comparison from a very high percentile of precipitation, so very rare hourly precipitation, 99.9 percentile for northern Italy and surroundings. So in observations, we can reach values of 16 to 18 millimeters in an hour. And below, you see those regional climate models of 12 kilometers. In this case, we are nowhere near that. You only have half of the values. But with the convective permitting models, which is the figure on the middle, we can get much closer to it. We are already at intensities about 14 millimeters per hour. And also the climate change signal might be quite different. This is again a comparison between 12 kilometers and 3 kilometers for the intensity and the frequency of these very rare events. And even though the frequency is not too different, the intensity is. The intensity is much larger for these kilometers. And we tend to believe this more because they are better in representing what you see in the observations. So the question is now, how can we use this large amount of data that we are producing, typically on computing centers like in Hamburg, where we produce petabytes of data. So I will show an example of a project funded by the German Ministry of Education and Science, BMBF, which is called Regional Information to Inform Climate Adaptation. And I will show you an example that we did for our federal state in southwestern Germany, Baden-Württemberg, focusing on the region of Stuttgart. And this is an area which, of course, has a very large city, so it has a clear urban center, but there's also a large cultivated area and a lot of forests in the region. And also in terms of orography is quite different. And the consortium is built as follows. So we are, so to say, at KIT providing the climate information, the climate expertise in the consortium. This is the information is given to the impact models that they are producing, for example, risk maps for flooding under current and future climate conditions. And this is then taken to another step to other institutes and the city of Stuttgart that are developing adaptation measures, first quantifying the needs and then the adaptations. All of this is then quantified economically by another institute. And we put all of this information in what we call a climate atlas. So it is a GIS-based information system where all of us can access it, and hopefully it will also at least partially be open for the public to access it. And we are then interacting with the city of Stuttgart really to make decisions on what can be done and decided based on the work that we are doing. And we are now starting the second phase of this project. I will give you an example of the type of results that we can get focusing on heat waves and thermal perception. So I can always say this is an example of a heat wave index, which looks on how long the temperature itself is above a certain threshold and over several days. And for comparison, we use index for human heat stress, which is called the UTCI, that also considers humidity and so to say our perception on how comfortable we are in a certain situation, given a certain humidity, temperature, and wind. And the next slide shows you the projections, so to say, first for the recent past, for the near future, and the far future, the number of heat wave days in the summer in southern Germany. So nowadays, we have, with a meteorological index, something like 10 days on average. In the near future, I would say around 20, but if we go to the far future, this can get up to 50, 60 days. The interesting thing in this figure is that it is actually quite homogeneous, given the type of index that we are using. So it is quite a flat figure. This looks very different if we consider the index of thermal perception. So if you look at the recent climate, which is what it is in the end, you already see the difference between the Rhine Valley, which is in this light blue color, so the lower part of the Rhine, compared to the surroundings. So there already we can have about 10 days of high UTCI values under current climate conditions. And you see the projections for the near future and the far future. And what is different here is that, unlike the upper figure, we have a clear, strong orographic signal. So the whole thing, the existing pattern, is being actually intensified. And this is something we need to think about. So on the next step, and this is something which we are doing now, we are working with colleagues from the University of Freiburg to bring all of this climate information to the scale of the cities. And this is work that has been done. So this is the city of Freiburg. This is the location of it in Baden-Württemberg. And this is a map that was created with some dynamical modeling, but also with machine learning methodology, really to map over the city what is the number of hours that you can expect this high UTCI value, this high thermal perception values above 32 degrees in a year. So you have some areas like the old buildings district on the right, which is a bit higher, that the values are fairly low. But already now in the industry area, which is far north of the city, you already can have up to 500 hours nowadays with these very high values. And what we are doing with them together now is to run this through, is just to show you that we actually have this information on the meter scale, so we can really look at cities, canyons, and backyards and everything. So we have the full data. And what we are doing now is really looking, fitting this with the climate change scenarios and see how, for example, the number of hours or the number of days with these very high temperatures may change in the far future and the near future. In the last example, this is over 200 hours a year, which is quite a lot. And what we are trying to put together now, and this is my last statement, we are trying to develop an integrated modeling chain where we can bring the information from the global scale to the local scale to couple it with impact modeling and really help to develop adaptation and mitigation measures. Thank you.